Let's look at the basics of how centrifugal pumps function. A centrifugal pump, as you might expect, involves some rotation and some centrifugal force. The liquid that's being pumped comes in the center of this impeller, and it then flows outwards due to centrifugal force. Now we need to have some blades on the impeller to guide the flow to make sure that it does actually flow in an outwards direction as the impeller rotates around this way. So if this impeller is rotating and liquid is coming in the center here, it will go outwards centrifugally out, following the blades towards the outside of the impeller, driven by centrifugal force. And because the impeller is rotating, once it gets to the end here, relative to the fixed casing, the fluid is actually moving in this direction, around and out the discharge of the casing. So the result is the fluid comes in the center, it's driven out to the outside of the impeller, and it flows around this volute, which is the casing of the pump, that is increasing in cross-section to account for the fact that there's a little bit coming out of here, more coming out of here, so there's got to be room for all of it as we come around here. And finally, we've got flow coming out the discharge here. Now, terminology, we have the inlet in the center here, which is what's commonly referred to as the suction side of the pump. That's because it's sucking the liquid in to the center here. And the pressure in the center here can actually be lower, below atmospheric pressure, and possibly even low enough that we could get some boiling in the liquid. And we'll talk about that later, where we have to be careful that we don't get that boiling or cavitation. That inlet is in the center. However, sometimes we'll have a pipe flowing in this way, so-called end suction pumps. So the flow comes in this way and then it comes out going this way. And sometimes we'll have inline pumps where the inlet flange might be over here and somehow we've got a passage in the casing that is leading the liquid around the outside of the volute and into the middle here. And that's what we'll see in some of our configurations later on. The pump outlet is also called the discharge, and it's at the end of the volute. So it comes out of the volute, and that's this section here where we're coming out to this flange, and there'll be piping attached here, and it'll go off over this way. Now, as you can imagine, small pump, small flow rate, bigger pump, bigger flow rate. And if we wanted to scale up the flow rate, we'd find that if we increased the size of the pump, we'd have a flow rate increase because the velocity would go up. Or if we increased the speed at which the pump was rotated, we'd have a flow rate increase because the velocity would go up. So it's not too surprising that it scales with the velocity. Now the head, on the other hand, the amount of pressure rise generated or head rise generated by the dynamics in the pump is going to depend on the V squared over 2G type effects. It's a dynamic pump, so Bernoulli's equation is going to be important. And we're going to see head proportional to size squared or speed squared. So those are going to go up even more if we increase the size or the speed of the pump. And of course, the power that it takes to drive the pump will depend on the amount of useful work that we're doing with the fluid. And when we do work on a fluid, we see a pressure rise, a rho GH type pressure rise, and the flow, the rate at which we're pushing volume out the end. So we see a PV work term, and the power taken to drive the fluid out of the pump depends on density, gravity, the head rise across the pump, and the flow rate through the pump. So those are the conditions that we'll see with just about any centrifugal pump. And you'll find out a whole lot more about that kind of behavior if you take more advanced fluids courses, particularly if you take a course in turbo machinery, which will cover pumps and turbines and the nature of the shape of these blades and their curvature and a whole lot more details than we can get into in 241. But for the moment, let's think about a pump And what happens when we turn it on? Well, if we're going to be able to control the system, we're always going to have a valve on the discharge of the pump. So before I turn the pump on, the valve will be closed. So the valve is closed, I turn on the pump, and the valve is still closed, so there's no flow going through. So Q is equal to 0, but H is quite high. The pump will be spinning around, will generate quite a lot of head rise across the pump. There'll be quite a bit of pressure here pushing against the valve, trying to drive the flow through the valve. And of course, because the valve is closed, there'll be no flow through the valve. If we crack the valve open a little bit, so just opened a little bit, then we'll get a small flow going through. We'll still have a high pressure here, but we're letting a little bit of flow come out, and we'll have a similar H value. The pressure is still really high here. If we open the valve a little further, then Q will get bigger, and the head will get a little bit smaller. It depends on the geometry of the pump. But let's look at the relation here. If we looked at head versus flow, and this is the classic curve that we'll draw for any pump situation, then when we start here, we may have quite a high head and no flow. That's because we've got our valve closed. So that's that location there. And as we open the valve a little bit, we will get some flow going out, so we'll move up along the Q axis, and depending on the geometry and details of exactly what's inside the pump, we may see the head actually increase or stay the same or possibly decrease, depending again on the geometry and the details that you can figure out more about in a turbo machinery course. Let's say it increases, we'll hit a peak, but eventually the head is going to be decreasing as we have increasing flow. And finally, once that gate valve is fully open and there's almost no head rise across the pump, all of the energy of the pump is going into just driving the flow through and out the other side, then we'll get down to about here. This is the highest flow rate we could get with that particular pump at no head rise across the pump. So anytime we're operating this pump, we'll wind up being somewhere along this curve. We could have a high head and a relatively low flow, or a high flow and a relatively low head. But we'll be somewhere at one of these data points along this curve. Now this pump casing is designed to accommodate just this particular size of impeller just beautifully. Now if we increased the size of the impeller in the pump casing and went up to the maximum that we could possibly fit, we might be able to get some more additional flow and head and get a curve something like this with an oversized impeller. So that's not going to be necessarily ideal, but it is a way of getting some more flow out of this pump by just increasing the impeller diameter a little bit. So our perfect best design, that might be the most efficient operating point here. That might be the best operating for this pump. It's at a medium level of head and a medium level of flow. And if we go to a lower flow rate, our efficiency may go down. Go to a higher flow rate, our efficiency is going to go down. Go to an oversized impeller, our efficiency is going to go down. We could also go to an undersized impeller. We could keep the same pump casing and go to a smaller impeller, in which case this undersized impeller would generate a lower head at the various flow rates along the way. So this is a way that we can do with just one pump casing, one casting that we can build. We can get various different pump performance curves out of it. But this head flow curve is the primary information that you need to know about a pump to know how it's going to perform in conjunction with a piping system. We'll look at some of the manufacturer's curves, because the way you get these curves, you measure them. And the manufacturers will provide curves that say, this is the performance characteristic for our pump, and they should be able to guarantee them for you if you buy their pump and put it into service. So we will always go to the manufacturer's pump curve in order to get the actual performance information that we're looking for to base our designs on. So there you have the basics of centrifugal pumps. That's an awful lot of what you need to know in order to be able to select pumps. And we'll cover some more of those details in subsequent videos.